Now we'll talk about an example of a quantum system, and one of the easiest examples we can think of is the single spin 1/2 particle. So if I have a single spin 1/2, that means I'm going to have a single moment for this spin. So it corresponds to a magnetic moment, let's call mu 0. And I can talk about a quantum number in order to specify the state of the system. So I'm defining this quantum number sigma such that sigma is equal to +1 if the magnetic moment is up, and it is equal to -1 when the magnetic moment is down. So I can figure out the energy of the system when there is an applied magnetic field. So if there is an external magnetic field that is in the up direction, and the state of the system is such that the quantum number sigma is +1, that means the magnetic moment is pointing up. That means the magnetic moment is parallel to the magnetic field, and the corresponding energy of the system is going to be given by minus mu 0 b. Remember, this is minus mu dot b. Basically, it's the dot product of the magnetic moment with the magnetic field. So it will be given by minus mu 0 b. And if I have the other situation, magnetic field, external magnetic field is up, the state of the system is such that sigma is equal to -1. That means the magnetic moment is pointing down, anti-parallel to the applied magnetic field. This will imply that the energy of the system is plus mu 0 b. So if I show this on an energy level diagram, so here is the energy of the system, and there are two possible quantum states. One quantum state has mu 0 magnetic moment pointing up. The corresponding energy is minus mu 0 b when the quantum number sigma is +1. And if the magnetic moment is pointing down, the corresponding energy is plus mu 0 b, higher than the previous one, and the corresponding quantum number is -1. And once again, this is true when the external magnetic field we're applying is pointing up, in the up direction. So we can see that there are two energy levels corresponding to the quantum states that are specified by sigma. So by specifying the value of sigma for the system, I specify the quantum state of the system. Now if I generalize this to a system of n spins, so if I have a system with n spins, then what would happen? I have an ideal system, so these are spin 1/2 particles, fixed position, and they are far enough that the interaction between the spins can be neglected. So I have an ideal spin system. Now if I specify a quantum number for each spin, so similar to the previous case, for the ith spin I can specify a quantum number sigma to be plus or -1. Again, +1 means moment is pointing up, -1 means moment is pointing down. And the state of the system the quantum state of the system can be specified by giving a list of numbers. So this is specified by giving you a list, the value of sigma 1, the value of sigma 2, all the way up to the quantum number of the capital Nth spin in the system. So this basically specifies the state of the system. Now, let's look at a concrete case for n equals 4. So I have a 4 spin 1/2 system. So let's think about the value of sigma. So instead of using plus minus 1, I will just use a plus or minus to represent the value of sigma. So if sigma 1 is plus, sigma 2 is plus, sigma 3 is plus 1, and sigma 4 is plus 1. When I add them up, I will get a total magnetic moment of 4 mu 0. Since they're all pointing up and parallel to the external magnetic field, the corresponding energy will be minus 4 mu 0 B. Now I want to have one of the spins, one of the moments pointing down. So I will have first the fourth moment pointing down. So let's make this point down. Then I can have the third one pointing down. I can have the second one or the first one pointing down. And that basically exhausts all the possibilities in the scenario where I have one moment pointing down. So 3 pointing up, giving me total of 3 mu 0, 1 pointing down, minus 1 mu 0. The total magnetic moment in this scenario would be 2 mu 0. So if I have a total magnetic moment of 2 mu 0 pointing up, the corresponding energy would then be minus 2 mu 0 B. Now I want to have two of them pointing up, two of them pointing down. So let's have the first one pointing up, second one pointing up, third down, fourth down. The first one up again. The second one is down, third one is up, and the fourth one is down. The first one is up again. Now this time I can have second one down, third one down, fourth one up. And now I look at the scenario in which the first moment is down. So 3 cases where I will have the first moment down. Then I can have second up, third up, fourth down. Then I can have the second up, third down, fourth up. Then I can have the second down, third up, and fourth up. So basically I have a total of 6 possibilities that corresponds to this scenario. The total magnetic moment, because 2 pointing up, 2 pointing down, gives me a total of 0 magnetic moment pointing up, corresponding to 0 energy. And now I have the symmetric case where I have 3 of the moments pointing down, 1 pointing up. So I can have the first one up, second one up, third one up, or fourth one up, and then the rest of the moments should be down. And this is going to correspond to a scenario where I will have minus 3 mu 0 plus 1 mu 0, total of minus 2 mu 0 for the total magnetic moment. Since the net moment is pointing against the applied magnetic field, anti-parallel, the energy is high, plus 2 mu 0 b. And finally, if I have all of the moments pointing down, it would correspond to a total moment of minus 4 mu 0, and the corresponding energy would be plus 4 mu 0 b. Now if I want to show this on an energy level diagram, so here is the energy. Which one is the ground state? The ground state, remember, is the one that has the lowest possible energy. So the one that has the lowest possible energy is the first one. So there the corresponding energy is E0, which is minus 4 mu 0 b, and this is a non-degenerate quantum state because there is only one quantum state that corresponds to the ground state. Now I can have a higher energy term, a higher energy state, that's number 2, 3, 4, 5. So R here represents, once again, the quantum state number. Okay, and now for this quantum state, R equals 2, 3, 4, and 5 quantum states, I have the same energy, minus 2 mu 0 b. So here is one of them, 1, 2, 3, 4. The corresponding energy for this first excited state, E1, is minus 2 mu 0 b. And when I move on to the next possible higher energy state, I have quantum state numbers 6, 7, 8, 9, 10, and 11 corresponding to this scenario. Here I have 6 possibilities. So here is 1, here is 2, here is 3, 4, 5, 6, giving me a total energy of 0. Once again, it's a degenerate state because I have 6 states corresponding to the same energy level. Then I have one that has 4 states corresponding to the energy of plus 2 mu 0 b. So I can have 1, 2, 3, 4 levels corresponding to the energy E3 plus 2 mu 0 b. And finally, I can also have a non-degenerate state for the highest energy level. So this would be the last one that has energy E4 corresponding to plus 4 mu 0 b energy, which is the fourth excited state for this 4 spin 1/2 system. So just to summarize, let's take a look at what we did. So we're trying to find out the specification of the state of a system. For a quantum system, a single spin 1/2 particle which has a corresponding moment mu sub 0, if the moment is pointing up, I call a quantum number that specifies the state of the system, sigma, equals to plus 1. If it's pointing down, then it's minus 1. Now we know from electromagnetism that if the magnetic moment is parallel to the applied field, the energy is negative, minus m dot b. If it is anti-parallel, then the energy will be higher, plus mu 0 b for this scenario. So I have 2 energy levels. Energy level diagram shows me 2 states, 2 non-degenerate states. There's only one state corresponding to a given energy, plus mu 0 b or minus mu 0 b for the ground state energy. So I have 2 energy levels and 2 states, and the state is basically defined by this quantum number sigma. For an n spin 1/2 ideal spin system, where the spins are in fixed positions and no interaction between the spins, then I can specify the state of the system by giving you a list of quantum numbers. The sigma I for the ith spin basically tells me if the moment is pointing up or down. So sigma 1, sigma 2, all the way up to sigma sub capital N gives me the state of the system. For a specific example, I consider the 4-spin 1/2 system. There are the following possibilities: all moments up, 1 down, 2 down, 3 down, and 4 down. So I have 1, 2, 3, 4, 5 possible scenarios, and corresponding to these scenarios, I have different energy levels. So here is the energy level diagram for this 4-spin 1/2 system. I can see that there are two non-degenerate states corresponding to energies of plus 4 mu 0 b and the ground state minus with energy minus 4 mu 0 b, and then I have 4 degenerate states at energy level E1, 4 degenerate states at energy level E3, and 6 at energy level E2, which has 0 energy. So E1, E2, E3, E4, these are corresponding to first, second, third, and fourth excited states.